going. So, hopefully, in these few minutes, I've at least persuaded that machine learning is intriguing and potentially worth studying. So now let's start studying it. What is machine learning, right? How do you do this amazing thing of getting a computer to program itself? And if you're interested in machine learning, if you just decided that, for example, you might want to use machine learning in your problem of interest, in a way, it's kind of hard to get your bearings because, many of the textbooks are pretty impenetrable for someone who doesn't already have a lot of mathematical background and whatnot. And then if you look at the literature, right, what you see is like there's tens of thousands of different machine learning algorithms. And this is, of course, a very active area of research, and, there's thousands more coming out every year, right? So the number of machine learning algorithms seems to be growing exponentially, and now how do you get your bearings, right? Do you have to learn each one of these new things or, face doing the wrong thing or being out of date? Actually, you don't, right? And this is one of the first things that, I think you can take from this class. It's the following. Machine learning algorithms are essentially just combinations of certain components. And if you understand what those components are, then this combinatorial space of machine learning algorithms becomes a much smaller space of the components, and then you can combine them in different ways. Okay? So you want to know what those components are, and you want to know how they go together. And then as you hear things about machine learning and you see new things coming out, now you have a way to keep things organized and to not get overwhelmed. Okay? So what are those components? They're basically three. Almost all machine learning algorithms have these components in one form or another. They are representation, evaluation, and optimization. Okay? So let's look at each one of these and see what it is and what examples of it are. So representation. If your computer, right, if your machine learning program is going to create its own program, the first decision that needs to be made is what language this program is going to be in. Right? Like you as a programmer might decide, well, I want to use Java, or I want to use Perl, or I want to use whatever. Right? There's a similar decision to be made by the machine learning algorithm or by you for the machine learning algorithm. Of course, the languages in this case are not going to be things like Java, etc., which are designed for humans. They're going to be languages that hopefully are good for the machine learning program to use. So what are some of those languages? Well, here's one, decision trees. Decision trees are the first one we'll study, and they are, according to surveys, by a good margin, the most widely used representation. Okay? And by the way, roughly speaking, the way we're going to organize this class is by representation. So we look at each of these representations in turn and then see how we do the evaluation and the optimization with them. And also, as a rule of thumb, new representations come up much less often than new evaluation functions come up, which in turn come up less often than new forms of optimization come up. Okay? So in a way, the representation is the most stable core of machine learning. This is not to say that there aren't new representations to be invented. I'm sure there are, and I look forward to them. So here's another one that's also a very natural one. It's sets of rules. Right? You can think of a decision tree as being a set of nested if-then statements. That's at some level what a decision tree is. So it's just a basic programming construct writ large. Sets of rules are also if-then statements, except they're not nested. They're just, it's a sequence, right? The first one that fires wins. Or then you do some combination of the ones that fire. Okay? Sets of rules can be very powerful because, in particular, if the rules are in first-order logic, then they're also called logic programs. You can genuinely write any program in this way. Right? So it's very powerful. It's a very powerful representation. You don't necessarily want to write a program in this way, but in principle, there's languages like Prolog, for example, that can do anything under the sun, and we will see how to learn such programs from data. Another one, and in fact one of the oldest ones, is instances. This is the best of the laziness approach to machine learning. The instances approach is you just remember the cases that you saw. And then when a new test comes up, you just try to find the nearest case and you apply it. So you're doing medical diagnosis, you just remember all your past patients. And when a new patient comes in, you find your old patient that's most similar to her, and you apply the same diagnosis. Of course, there's many variations on this, and we will spend a whole a lecture on it. But the basic idea is joyfully simple and unsurprisingly powerful. So this is the use of instances themselves as the representation for what you want to learn. Then getting on towards more sophisticated things, there are a lot of approaches in machine learning that use probability. Right? Probability is a very powerful tool. It lets us deal with uncertainty. It lets us weigh evidence. It means we don't have to always be making black and white decisions. Efficiency is a big concern. Graphical models are a very large family of probabilistic models where I use a graph to represent the dependencies in my distribution. Okay? So we will also look at some of those, and in particular, there's two main families called Bayes nets and Markov nets, and we will see what some of them are. As some of you might know, the Turing Award this year was won by Huda Pro, a great computer scientist. His main contribution was, developing Bayesian networks. Neural networks, this is a very fun one. The idea in neural networks is let's reverse engineer the competition. Right? If you're going into market with a new product and the competition is way ahead of you, it's a very good, tactic to just look under the hood, right? See how they're building their cars and see if you can make yours the same, right? While they're behind, this is a good thing to do. And, make no mistake about it, when it comes to learning, we are way behind ourselves. What does that mean? We, as the producers of machine learning programs, are way behind ourselves as humans. The human brain is the most amazing machine learning system ever invented. And other animals too, for that matter. Okay? The human brain is really doing something extraordinary, and we haven't figured out what it is yet. If we did, that wouldn't be worth 10 Microsofts. It would be worth, 1,000 Microsofts, or, the whole world economy potentially. So the idea in neural networks, and of course the human brain is a network of neurons, hence the name neural network. So the idea in neural networks is let's look at what the human brain does, and then let's see if we can turn that into an algorithm, right? Very seductive idea. Again, we will spend a week seeing how we can do this and the state-of-the-art things that come out of it. Even more recent, so all of these approaches, have been around for, decades. They continue to be developed, right? So new algorithms in any of these families continue to appear. Here's one that, became popular more recently, but is also very, very powerful, and this is support vector machines. Support vector machines, in a way, are a more powerful version of instance-based learning, but they are quite powerful. They are different from some of the other methods in that they use much more sophisticated mathematics. And many people just use them as a black box because often they work very well, but it's a pity to have to use them as a black box. And we in this class don't want to use anything as a black box. We want to understand how things work so that we can change them, make them fit our needs, and then tomorrow when new things come along, we want to be able to then understand those as well. So what we will do when we study support vector machines is we will cover just enough of the mathematical background that you can see what support vector machines are doing and why. Okay? And then one thing that people have also found in recent years is that the best thing that you can do when it comes to learning is not to learn one program or one model, but learn a whole bunch of them and combine them. This is the wisdom of crowds applied to algorithms. It's the wisdom of algorithms, right? Often you have many people vote on something, they come up with a better estimate than any individual person. The same thing is true of machine learning algorithms. If you run 100 algorithms with 100 different conditions, each one of them, and combine the results, you will usually get better results than if you just run one of them. This is very powerful. For example, the Netflix prize was won, and the second place was also systems that combined a lot of different algorithms. In fact, what both of these teams were doing was competing to see who could aggregate the most people quickest. They all started out being small groups competing with each other, and then they realized that by aggregating they could do better. So they wound up with larger numbers of things being combined than ever before. And I think in the future we're going to see more of this. So being able to create model ensembles and smart ways to do it is a very important topic. It's often a very easy way to get a large extra payoff after you've put all the work into developing algorithms and trying different things. Instead of picking one, combine them. And we will also see how to do that. Okay? So these are the main things that we will cover here, but not all of them. Okay? But this at least gives you a flavor of the kinds of representations that get used in machine learning. Okay? Questions so far? All right, but of course, once you've picked a representation for your program, your work has just begun, right? Sure, you've picked the language. Now what? Well, this is where the next thing comes in, and the next thing is evaluation. What the machine learning system is going to do, right, is generate candidate programs, right? From the data, it's going to, according to some algorithm, generate a candidate program, right? Is this what you want? These were the inputs and outputs that you gave me. I have just created the program that seems to pretty well transform these outputs into those outputs. Is this what you want? Right? Now, if you could personally inspect every program that the machine learning system generates, fine. But of course, you don't want to do that. It's going to generate easily millions of candidates. So what we need is an automatic way to evaluate the program. Okay? So the next big choice is the choice of your evaluation measure. How am I going to gauge that version A is better than version B, and therefore select version B, and then maybe try variations of B, C, and D, and select one of them. Okay? So here are some of the measures that people use. The first measure is accuracy. Very simple. Out of those examples, how many of them did you get right? Right? Let's say I'm an email provider, right? And I have lots of examples of emails that are spam and not spam. I know which ones are spam because the users, conveniently mark them as spam, right? And now I create a program that predicts whether something is spam or not, and the accuracy is just a fraction of the spams that it marks as correct, plus the non-spams that it correctly marks as non-spam. Okay? So this, or like the fraction of diagnoses that were correct, or the fraction of your credit cards that you wish that they really did not, go bankrupt and so forth. Okay? So this is the simplest measure. Two other measures that are often used and that are very popular, for example, in things like information retrieval applications, are precision and recall. Okay? Precision and recall are a lot like accuracy. Precision is out of all the fraction of things that you predicted were yes, how many of them really were yes? So what fraction of your spams, of your predicted spams, really were spams? What fraction of the pages that you said were interesting really are interesting? And then recall is, out of all the ones that really were spam, how many did you identify as spam? Okay? So notice that these two measures are complementary and you really want to do well on both of them. The reason these measures are useful over something like accuracy is that in many domains there is a very large number of true negatives. Most of the things are false, they're not interesting, and you don't want to mark them as interesting, and you won't, and you want to ignore those. Accuracy doesn't ignore those, precision and recall do ignore that. Okay? Now, if what you're trying to predict, instead of just being yes, no, like spam, not spam, or interesting, not interesting, it's something like a rating. Like, for example, if I send my catalog to this consumer, how much will they buy? In this case, you're predicting the numeric quantity, so you want a measure that varies with how much of an error you make. Again, there's many things that you can use here, but the most popular one is squared error. So it's the sum over all your examples of the square of the difference between what you predicted and what the true value was. Okay? When you're building probabilistic models, where what you're trying to do is trying to predict the probability of something, for example, what is the probability that this page is interesting, then the standard measure to use is something called likelihood, which you may remember from Statistics 101, but even if you don't, we will go over it here. Right? Likelihood is basically how likely is what you're seeing according to your model. If what you're seeing is unlikely according to your model, your probably is not a very good fit to the real world. If what you're seeing is very likely according to your model, then your model, to the best of your knowledge, probably does fit the real world well. Okay? So that's the idea of likelihood. Likelihood is often good when your learner is not very powerful, but when your learning is powerful, it's very you could get by a very high likelihood by just memorizing your examples, and then you don't generalize, but you want to generalize. One way that you have of generalizing or of helping to generalize is, instead of using likelihood, use what is called a posterior probability. Again, we will look at the details of this when the time comes, but the posterior probability is a combination of two things. One of them is the likelihood, and another one is the prior probability. The prior probability is how likely you think something is a priori. This is where you get to put your knowledge, your expert hypotheses, your assumptions into the system. Or one way, you can put them into your prior. Before you've seen any data, you believe that certain things are more likely than others. That's your prior distribution. And then when you combine that with the likelihood, you get your posterior, and then it's the posterior that you use to evaluate your models. Okay? So when you're using prior probability, you're actually evaluating your candidate programs using a combination of the data and your own beliefs about the problem. Okay? So this can be very powerful. It can also be complicated, but we will see how to do it. So, these are all things that people have used for a while. But here's something that people discovered when they started applying, machine learning in practice, on a big scale. They often found that these algorithms, the machine learning algorithms, were not really producing what they needed. And the reason for this, a very common reason, was that if you look at something like accuracy, right? what percentage of my spams or non-spams did I predict correctly? You could actually be very accurate and yet be doing a very poor job. For the following reason, is that the cost of a false positive, saying that something is a spam when it isn't, can be very different from the cost of a false negative. Something that is not a spam and you say it is. Okay? Or sorry, something that is a spam and you say it isn't. Okay? If something is a spam and you say it isn't, well, then it just gets through and annoys the user a little bit. Small cost. If something is a message from your boss saying, I need this by tomorrow, and then you're fired if you don't do it, right? And that gets tagged as spam because it has too many exclamation marks and too many words in capitals, right? This is like a realistic thing, right? Then you could lose your job because of that, right? So the moral of the story is, you want to be conservative. You want to err on the side of predicting that something is not spam. And as it turns out, this is a very, very common thing to happen. For example, if you have a test for AIDS or for cancer, right? You might want to err on the side of telling people, yes, you may have cancer, do another test, as opposed to letting them walk away with the cancer and die. Okay? So the moral of the story is we want to take cost into account when making decisions, and ideally we will actually do that right inside the learning algorithm itself. So this is another type of measure that you could use. More generally, you could use what in decision theory is called utility. Different decisions, different outcomes have different utilities. And what you want to do, right, this is what being rational means, is you want to make the decision that maximizes your expected utility. So this is your average utility over the outcomes that could happen. Okay? And again, you could use that a posteriori, or you could use that inside the learning algorithm. More recent things use even funner ideas, like for example in support vector machines, we use the margin. The margin roughly has to do with how far you are. When you make, for example, a boundary between on this side it's spam and on this side it's not spam, I would actually like my boundary to be as far from any given example as possible, right? Because if it runs very close to an example, maybe that's not quite where the boundary should be. So that's another thing, another measure that you can use. And then there's the ever popular measures that come from the area of decision theory, of information theory, right? Information theory has lots of interesting notions like entropy, right? The information content of some variable. KL divergence, also known as the relative entropy between two variables. We can also use these to guide our learning, and indeed we will see examples of that. Okay? And there's many more. Again, people come up with new measures every year. These are the more popular ones, and we're not going to cover everything, but it's good to have a notion of what some of the main things are. Okay? Often an exercise you can do is you can take an algorithm using one of these measures and change it to use another measure and see what has to change in order to do that. For example, you might try to turn an algorithm that is not cost sensitive, it's just maximizing accuracy, into one that is cost sensitive. Okay? All right, so we've chosen a representation, we've chosen an evaluation measure, but in some sense the most important part is yet to come. The most important part is, okay, so now how do I actually generate candidate programs? Okay? So that part is the optimization or search part, right? Now you need an algorithm that will actually generate lots of candidates for you that you can evaluate. And then finally you pick one of them and you return it to the user, and that's the program that you're going to use. Okay? Now, of course, if you had unbounded resources, you could just try every program on earth. But you probably don't want to do that because you don't have the resources. And in fact, even if you had the resources, you might not want to try that because you might overfit this and then get bad results that way, as we will see later. So what you want is some sort of smart search strategy that is clever about picking which programs to generate. And of course, this should be guided by the evaluation measure. Right? This is why we have the evaluation measure inside the system and not outside. Is my algorithm, such algorithm, is going to be evaluating candidates, picking some of them, and then generating variations of those and so forth. Okay? Now again, there's many different types of search algorithms that you can use, or optimization. People in operations research and continuous math tend to call it more optimization. In computer science we call it optimization or search, but it's really all the same thing. The type of optimization that you want to do naturally depends on what type of representation you're using and what type of evaluation measure you have. In particular, if your representation is discrete, what you need to do is combinatorial optimization, right? What you do is this process of combining pieces into larger pieces, see how good they are, taking a piece, modifying it, see how good that is, and so forth. The simplest type of combinatorial optimization is just greedy search, right? It's what I've been using as an example. You generate a candidate, you see how good it is, you generate 10 candidates, you pick the best one, and then from that candidate you generate 10 more and you keep going, right? This is the research, but there's many other types of combinatorial optimization that you can use. If you have numerical parameters to optimize, which many machine learning algorithms, if not most, do, then what you use is what's called convex optimization, or it's really just numeric or continuous optimization. Convex is a technical term that, and we will see what it means later on. The simplest form of convex optimization is gradient descent. It's the continuous analog of greedy search. Gradient descent is, if you want to find the valley, just let the ball roll down the hill. That's what it is, right? Wherever is steepest, it's where we'll go. Okay? This is good for a lot of things, but it's also pretty crude it can fail in many ways. It can be very, very slow. It can get stuck. So we will see some better ways of doing convex optimization. And finally, particularly most recently, people in machine learning have started using a lot of constrained optimization. So what is constrained optimization? Constrained optimization, in a way, is a combination of combinatorial and continuous optimization. It's continuous optimization where you are subject to constraints. I have this surface, right? I'm not trying to find my optimum in that surface, but I'm trying to find that optimum subject to staying within a certain box. Okay? And this box is what the constraints are, right? A famous example of this is linear programming, right? I have this linear function that I'm trying to optimize. I'm trying to optimize my profits from my factory or whatever, but I have these constraints on how many machines I have and how many things I can produce an hour and the cost of the components and whatnot. Okay? So I'm trying to optimize a function subject to constraints. If the function and the constraints are linear, then what we have is linear programming, but there might be nonlinear as well. And some of those techniques get used in machine learning. Okay? So again, this is just a very brief overview of the space, but I think it's very important to have a map of the territory before we dive in, right? What we're going to be doing most of the weeks of this class is looking at specific representations and the evaluation and optimization algorithms for them and the issues that arise, but at this point, we at least have a general map of the territory. Okay? Questions so far? Okay.